So yeah, my name's Stefan Smolenaers. I'm from InvertedPower, based in Melbourne, Australia. So sorry if I sound a bit groggy at the moment. It's 3:30 a.m. and I haven't slept yet, so it's quite a late night for me. But yeah, so Ted asked me to present sort of the concept of onboard charging, specifically powertrain integrated charging, and then go into sort of the work that we're doing here at InvertedPower. So I wanted to give some context first around maybe a purpose for the presentation. This was some DOE funding that Ted put up last week for reducing the cost of DC fast charging equipment. I think that this could be very well applicable to that, so maybe keep that in the back of your mind as I go through the presentation. But first, what do I mean by powertrain integrated charging? Well, it's effectively using the traction drive of an electric vehicle, which every electric vehicle must have, as part of the charging circuit. So the operation between driving a vehicle and charging a vehicle are mutually exclusive. We're never sort of plugged into the wall and driving the vehicle. So it means that we can exploit those power electronics that we have on board the vehicle for propulsion as part of the charging circuit. To give a bit of a sort of a understanding of what that might look like, it's not just the powertrain electronics per se, it's also the balancer system. So when you combine it all in, it's actually a lot of components that are currently being duplicated in, let's call it the status quo of charging, how you have a external box full of active power electronics. The majority of those electronics which we're duplicating in the infrastructure are already on board the vehicle. So we just need to be able to unlock that potential to use that as part of the charging circuit, and we can effectively save a lot of money in the deployment of EV charging infrastructure. So to give a visual representation, this is the status quo. You've got your big fridge size unit, which is your external DC fast charger, which has all your active electronics. It negotiates with the vehicle, specifically the BMS unit, I guess, to work out what the parameters are of the battery and what the charging parameters must be, to be able to charge it safely. But all the conversion happens off board. So the first thing is to realize that, yeah, we have this power electronics on board the vehicle, which aren't being used, and they're perfectly matched for the vehicle. So a 400 volt vehicle will have a 400 volt powertrain, an 800 volt vehicle will have an 800 volt powertrain. The power levels match the battery perfectly, and it already has communication with the battery management system and everything. So it's there ready to be exploited. So if we sort of look at which components there are specifically which can be replaced, and that's your active power electronics, it's the cooling system, it's the control structure, it's everything I showed on the previous slide. And if we do unlock that potential, it enables us to make charging infrastructure, optimized charging infrastructure, which is significantly smaller and cheaper. So by some of the calculations we've done, we're looking at order magnitudes in terms of cost reduction and size reduction. So it's very significant. The idea of integrated charging is not a new topic. It's been going for quite some time. People realize the potential is there. The first iterations were always focused on charging from AC. I want to focus on charging from DC because that's sort of a new area of development, maybe in the last couple of years, versus AC charging, which we've been trying to do for the last 10, 15 years. I'll give a shout out here to Wally Rappel. I've seen him on this chat before, on this this working group. And Tesla actually used to use a system that he was the inventor of. So a powertrain integrated AC charger using an AC propulsion system. They called it reductive charger. That was effectively this concept. So using the powertrain as the charger. The Renault Zoe still uses this concept. They still to date have the highest power charger on any passenger vehicle EV at 43 kilowatts. EPC Power, which is a California-based company, has an inverted charger unit, which I think is on the TransPower trucks. BYD have a fairly famous solution, an 80 kilowatt onboard AC charger, which again uses the powertrain. I'll talk a little bit about that one today. And then I want to talk about the DC charging solutions, which will be the Hyundai solution, which only got announced about 6 months ago, and also the Hitachi ABB solution, which has been going for a couple of years now. So first talking about the BYD solution. So BYD, probably the second biggest electric bus OEM globally. They sell about 10,000 electric buses per year, so very high quantities. And one of the main reasons why BYD do so well is that they provide this easy charging. They're the only ones to offer AC charging in commercial vehicles. Well, not the only ones, but probably the main ones to offer AC charging. So when you have a customer looking at different vehicle sets, if they buy a competitor to BYD, they know they have to install this fridge style unit, which costs tens of thousands of dollars, if not hundreds of thousands of dollars. It takes up significant space at the depot. Yeah, it's expensive and big versus the BYD solution where the charger's on board and all you need is the AC EVSE, which is very small, very cost effective, just a couple of $1,000s. It mounts on a wall. The installation is easy. So it's the ease of this solution which makes it so appealing. But today I also want to talk about how we can do a similar thing for DC. So there's no reason why, with the AC EVSE, all it's doing is bringing in AC. It does the communication layer, it does your protection layer, insulation monitoring, earth leakage detection, that sort of thing, and just passes through the AC. There's no active electronics in there. But if we have an onboard DC charger, we can do the same thing with a DC EVSE. We just pass through a DC source, and DC sources are becoming more common. we see a lot of site deployments with solar and storage. They're all DC sources. The AC is becoming less prominent, and the DC is going to become more important in the future. So if we can do such a thing where we have a DC EVSE as a very low-cost solution for interfacing with DC sources like solar and battery, we too can have a very small, slimline solution for DC fast charging at very low cost. And now I'll highlight the Hitachi solution because they're one of the few to actually have already done this. So it started off as being called ABB Tozer. So it's a trolley bus replacement where they've replaced the overhead wires with opportunity charging at intermediate stops. It's a 600 kilowatt 20-second flash charge. They call it flash charge, and obviously that's not a lot of energy that you can transfer in 20 seconds. So then they need to charge frequently. So in this bus route in Geneva, it's a 12-kilometer bus route. They've got 13 charging locations at 600 kilowatts. So in the traditional sense, where you have the charger off board, people must think they're crazy to have 13 600 kilowatt chargers along a bus route that's 12 kilometers long. It just seems cost prohibitive. But the secret here is, well, the charger is actually on board the bus, and it goes anywhere the bus goes. So it's actually quite cost effective to just supply it with power at these charging at the locations, at the stops. So the cost per additional charging location is not as significant as having external charging equipment. So that's the real secret sauce of the ABB Tozer or Hitachi eMotion Flash solution. And they've done really quite well with it. So in 2018, they had 12 buses in Geneva after the initial pilot. 2019, they sold a further 22 buses in Nantes. Now they've got 49 buses coming to Brisbane in Australia. They've just signed agreements with King Long in China and Ashok Leyland in India. So it really is becoming, this onboard DC charging. It's a new technology, but it's really starting to spread out and really gain some adoption because of the cost benefits. Yep.
Just to be clear, you're saying that they supply this with constant voltage DC, and the electronics on the bus does the current limiting, right?
Exactly.
Okay,
yeah.
Interesting.
So the next slide, this is actually from the Hitachi ABB marketing, which shows exactly that. So in the top right would be your traditional charger. You've got the offboard charger, you've got a pantograph, and then you've got the bus, which is just a dumb load in this case. Except for that, you need to initiate the communication between the bus and the charging station to make sure they're compatible, and then also to command the charging station at what charging power and current or voltage must it charge the battery at. Hitachi reckon that takes about 35 seconds just to do that communication, and they want the whole charging event to take 20 seconds. So obviously that's not going to work for them anyway. But in the bottom right is that the solution that they're actually using. When the vehicle stops and it plugs in, the powertrain electronics, and in this case they've got two 300 kilowatt drives to make a 600 kilowatt onboard charger, that reconfigures its mode from DC to AC to DC to DC, and they just charge from a stabilized voltage. In this case it's a controlled rectifier, but they have other alternatives which we'll go through soon. But yeah, I mean, they put the advantages there is the reduced time to charge, because you can charge immediately after the connection is made. There needs to be no communication between the charging station and the vehicle. The vehicle already knows the battery and what charging parameters are required. You've also got the reduced space. So the BYD solution, the charging infrastructure is reduced in size. So you've got the higher charging density, but you also have redundancy. They left that one off, but that in my mind is a big one. If you only had one charging station and 10 vehicles using that charging station, if that goes down, your whole operation stops. Whereas in this case, you've got 10 chargers and just one power source. So if one of your chargers goes offline, then you just lose one of your vehicles.
So this is, can I ask a question?
Yeah, sorry.
So can you go back to the previous slide?
Sure.
So this is an additional DC-DC. They're not using the propulsion machine, right?
No, they're using the propulsion machine. So in the middle thing where it says flash charging with extra DC to DC, that's showing adding an additional DC to DC onto the vehicle, which is obviously adding cost and weight and space to the vehicle. In the bottom solution, we're using the propulsion system as the DC to DC. So you're not adding that cost. Yeah. Mm-hmm. So they've got a few different options of the infrastructure. So obviously with a 20-second 600 kilowatt flash charge, that's a very high peak demand, but then maybe another bus doesn't come for another 5 or 10 minutes after that. So you wouldn't want to directly draw that from the grid, because then your peak demand charges are going to be through the roof. So what they do is, I mean, they only need a stabilized voltage from the infrastructure. So they can employ just a battery in the infrastructure. That becomes a charger. So they have a little 50 kilowatt charger constantly recharging this storage system, a battery. And then when the vehicle comes, it does a 600 kilowatt battery to battery fast charge. So the grid infrastructure never sees the full 600 kilowatts. It only ever sees 55 kVA or about 50 kilowatts. It does the automatic peak shaving, and also means, we can connect now to a low voltage grid rather than getting our own feeder and a medium voltage connection or whatever would be required for a higher power connection. So this would give you your lowest total cost of ownership. You reduce your installation requirements by going low voltage, and you're also reducing your OPEX by going, reducing the peak demand and increasing your load factor. They've got another version where you would have like at a terminal where multiple buses would be using the same infrastructure. It has a much higher duty cycle or use of the infrastructure. Then you can draw it directly from the grid. In that case, you're just using a standard IGBT rectifier and a filter, and just to create a voltage source, and the vehicles charge themselves. So very cheap, very dumb, and these are commodity products effectively from rail. The same with the depot infrastructure. You would just have basically a rail rectifier, transformer rectifier, and a plug. Very cheap. You know, these things have been around for hundreds of years from rail infrastructure, and they're in mass production, very reliable, strong supply chains, maintenance, everything. So it's a very robust solution. Much more mature than EV charging stations, put it that way. But if we're saying we can use rail infrastructure to charge the buses, well, why can't that one
is the galvanic insulation missing on the middle option?
They claim they don't need it. So you won't. Galvanic isolation is not necessarily mandated. In the CCS, in the Charin IEC standard, I think it requests galvanic isolation. In the SAE standard, as far as I'm aware, there's no requirement for galvanic isolation.
That's also mandated.
It is? Okay.
Well, yes.
These guys with the Hitachi solution, they're not complying to either the Charin standards or the SAE standards. They have their own proprietary solution for this. So no, they don't use galvanic isolation when it's just one vehicle charging. In the depot solution, where they have maybe 5 or 10 vehicles charging next to each other, then they put galvanic isolation per vehicle. So you can't get like a vehicle-to-vehicle potential.
Okay.
Yeah. So there's a research project in Germany which is reusing the light rail infrastructure to charge electric buses as well. So a similar thing where you have already a 750 volt stabilized source, and that's being used for light rail or trolley buses. We can use that same power source to charge EVs. In this case, when we have the DC to DC converter on board the vehicle, we can do that at no cost. But what I found interesting here out of this report was it says there's 4 gigawatts of installed capacity in German cities, and the utilization is only about 12%. So there's a surplus of 85 gigawatt hours that's not being used currently from that if you were at 100% load factor. So that would represent about 1.4 million EVs being charged every day out of that infrastructure without requiring any new hardware or installation.
That's a gold mine. That's a gold mine.
Yeah. But to be able to do that, we need to have an onboard DC on board the vehicle to be able to do it cheaply anyway. But it actually just so happens that new generation EVs will have an onboard DC charger on board every vehicle. So if you look at the Generation 3 EVs like the Taycan, the Audi e-tron, the Ioniq 5 from Hyundai, the EV6, they all have onboard DC chargers, 150 kilowatts or more at the moment. And anyone that's part of the Ionity consortium, so that's BMW, Daimler, Volkswagen, Ford, Kia, Porsche, Audi, they're all coming out with 800 volt vehicles, and they will all have onboard DC chargers. So we can exactly do that. We can charge from an unregulated DC source from using these vehicles. And the reason why they have it is because the 800 volt battery in these new generation vehicles is incompatible with the previous generation infrastructure, the 400 volt infrastructure. So they must have a 400 to 800 volt translation on board to be able to charge effectively.
So
Stefan,
Hyundai. I'm sorry to interrupt. So you're saying that these new vehicles, none of them they have an onboard AC charger. They're only provisioning the onboard DC charger.
No, they also have an onboard AC charger, but then they have this onboard DC charger, a high power charger. So the Taycan and the e-tron are 150 kilowatts, and the Hyundai, they haven't announced the kilowatts, but well, I'll just talk about this slide now, and Ted already discussed this one. They're also using the powertrain electronics as the DC to DC. So the same way that the Hitachi solution does it, they're doing the same method. And they only use one of their motors. They have a dual motor system. They're using the front motor, which is rated to 160 kilowatts. So we can presume that it's going to be a 160 kilowatt boost converter on here, DC to DC. And again, because they're using powertrain, there's no cost.
With PDE, can you hear me?
Yes, I can hear.
I was at Daimler Trucks before, so I have a little bit of knowledge on this as well. When we get up into larger vehicles, DC charging for the Class 6, 7, 8 vehicles will most likely not be present, so DC charging only. So it starts to make sense with the larger vehicles for sure. Yeah,
I agree with that. We'll go into more later. We'll talk a little bit about AC charging. So I'll talk a little bit about inverted power solution first. I'll just quickly go over this. I don't know how many power electronic engineers we have on the call, but this is your standard 3-phase drive inverter. Every electric vehicle has these components or some similar configuration of components. If we have a charger, and again, I'm going to focus on DC charging here. So we've got a DC plus and a DC minus. How can we configure that to the components with minimal cost to unlock the charging feature? With our solution, we're just adding one switch into the bus bar, about a $30 switch, very small, doesn't cost much, doesn't really affect the drive too much. And we can unlock this feature. So if we previously had a 300 kilowatt propulsion system, we now have a 300 kilowatt buck boost DC charger on board that vehicle, just with the addition of this switch. So that's the inverted power solution, which is slightly different to the other ones like the Hitachi and Hyundai solution. There's the current flow, how it would all work, operate for buck and boost. So we have a prototype drive that we can lend out to people. Our goal as Inverted Power is to not manufacture drives and sell drives. We're looking to partner with tier ones who are already sort of supplying the OEMs to provide this feature. So that's Danfoss, UQM, TM4, ZF, Cascadia, BAE, Cummins, or anyone that's providing powertrains to commercial vehicles. We want to work with them to provide this onboard DC charging feature. We want to make it ubiquitous.
So this is an inverter module. This is impacted proportion inverter with that with that relay.
Yes, correct. Okay. Yeah, so this is a 300 kilowatt drive inverter. We modified it with a relay, and it's now a 300 kilowatt charger or drive inverter in the one box. So we didn't increase the packaging size. We didn't do anything apart from add that one switch.
Sure, makes sense.
And we can lend this out to anyone who wants to do testing effectively. So it works with all motor types. There's no configuration required or change to the motor.
There might be additional switches to the DC charge coupler, right? There might be.
Yes, we would put, no, well, just your standard inlet CCS protection switches. Anyway, we'll move on. So also, we're not the only ones providing this. So Keeper have a drive inverter. Well, I don't know if it's on the market yet. This was an announcement from 2019 Busworld saying that, yeah, they're going to be able to use their inverter as a onboard DC charger and power levels up to 500 kilowatts. So they typically provide these to trolley buses. So to talk about some application examples, the Peterbilt 579EV, I took a photo of the specs from ACT Expo in Long Beach. It said it has 1.1 megawatts worth of traction. I see it maybe is now being revised down to 500 kilowatts. But if we go from the 1.1 megawatts of traction, if we turn that into a charger with the switch, that would be able to charge at 2.5C. I always do my fast charging calculations between 20 to 80% SOC. So that would give you 14 minutes as a fast charge, which doesn't fit with their 1 hour battery recharge time, which would be more like a 1C. But at 500 kilowatts, we're more or less around 1C. So that's a 30-minute fast charge, 20 to 80% SOC. So that seems pretty good. If you look at another example, the Tesla Semi, it's going to have, apparently it's 4 Model 3 motors. So that's about 1.3 megawatts of traction power. That'll give it a fast charging time of about 43 minutes. To go to Ted's favorite, this train, it's got 3.2 megawatts of traction power. So that gives it a charging rate 1.3C. So that's a 20 to 80% in 27 minutes. So it seems feasible to me that they could be using their traction power electronics. And if they're using the traction drives from ABB, I know ABB provide quite a lot of traction drives to rail applications. They could be using this technology. ABB already have this technology available, as we saw with the TOSA solution.
Yeah, just to feed in that Wabtec is the GE locomotives, so it's probably GE drives, but not to say that GE hasn't been using other people's stuff. But
yeah, okay.
Stating obvious, they're competitors.
Yeah. Okay, and we also get another advantage. So this talks to Ted's point about a Swiss Army knife, is that one of the issues that we saw with the passenger vehicle market is when you increase the voltage of the vehicle, that has knock-on effects with legacy infrastructure that we've installed. And people have spent a lot of money installing charging infrastructure, and if you make that outdated and not useful anymore, then someone loses a lot of money. With the onboard DC to DC, we can do that voltage translation. So say someone wanted to build a 1500 volt truck, which is the new Charin standard, is going towards 1500 volt, as we saw. If you built a truck at 1500 volts, it all of a sudden can't charge at your 800 volt charging station or your 400 volt charging station. Well, with the onboard DC to DC, we now have that voltage compatibility. So now we're decoupling the traction voltage from the charging voltage or from the charging infrastructure altogether. We're agnostic to whatever power source we get. As long as it's DC, we can charge from it. So effectively giving you that ultimate compatibility. So if we look at the different options that you could have as DC sources, it could be a battery, it could be an EV charger, it could be a rail rectifier, it could be a solar panel. As I mentioned, it doesn't matter as long as it's a DC source. So each one of these is going to have its own benefits. Like the battery is going to give you a lower OPEX because maybe you can do peak shaving with it. The solar panels gives you free energy. The rail rectifier is ultra low cost and high reliability from the rail infrastructure. The status quo EV charger, I don't see any benefits using that, to be honest. It's more expensive and bigger than all the other solutions and less mature technology. And now also these things are modules. You can make whatever you want into like a DC microgrid. So in this case, we've effectively made the ABB solution. You use a small rectifier to charge a battery pack, and then you bring your solar in as well, and then you charge from that DC microgrid. It's completely flexible. You could make whatever structure that you like, site specific. So you know exactly how much power you have on the AC feed, and then you can optimize everything around that. And you can also charge vehicles in parallel. So with the DC to DC on board, you could theoretically just add more plugs and charge them in parallel. We will need to get into the galvanic isolation topic, but theoretically you could put 100 trucks in parallel because every truck has its own charger. There's no additional cost apart from the $500 for the extra plug and protection associated. Effectively going back to...
You have to be very careful with your installation coordination, especially if you look at the existing infrastructure.
Yeah. Well, I would imagine you would still need the site-wide earth leakage to still be under the 20 milliamps or whatever the ground fault detection or interrupt needs to be. And that would become quite difficult with more trucks in parallel.
No, but also if you have now multiple sources providing short circuit current, you have to be careful. If you have an old infrastructure that's designed for 400 volts, it is designed for a different working voltage, so you have to be very careful. There are some caveats that you have to be very careful.
Yeah, and this is great stuff for the future gaps on codes and standards, saying what unintended consequences could happen if you reuse existing infrastructure in a manner not intended. And again, unfortunately, you guys are both Stefan. Both statements have good points. Anyway, go on.
Okay, so this was Ted's picture I just added in. Yeah, so we're using the DC to DC on board, and then it's this DC as a service model. We can do that, and I've already offered to provide in drives for that to test this concept. As we can provide our prototypes for this. So now to go into more structures with galvanic isolation. So if we were to use a traditional charger, in this case I'm showing a Heliox 150 kilowatt, we add on a battery pack to the output with a switch K1. So if we just focus on the infrastructure for now, we can have interoperability between a new fleet of vehicles with onboard DC chargers and an old fleet of vehicles without onboard DC chargers simply by switching K1. So if the vehicle has onboard DC charger, we switch in K1, we switch in this battery, and the vehicle can now charge from the voltage source of both the battery pack, which I've put as 2C, so 200 kilowatts, and the 150 kilowatts of the charging station in parallel, so we can get up to 350 kilowatts from that system. If the vehicle didn't have an onboard DC charger, it doesn't have the switch in it, then we open K1 and the 150 kilowatt charger can charge it directly. So we're providing that backwards compatibility or interoperability between fleets with and without onboard DC charging. And we can do this as a retrofit upgrade as well. Maybe you've already got a site with a 150 kilowatt charger there or a 50 kilowatt charger. You can come in and add this battery as a plug and play solution. We don't need to make any changes to the hardware or the infrastructure at all. This is purely a plug and play. And then if you bought a new fleet of vehicles or in your new fleet had vehicles with the onboard DC to DC, we can now boost the power output. So from 150, you could boost it to theoretically anything. You could boost it up to a megawatt if you wanted to. And same thing on board the vehicle. So with switch K2 in the drive inverter, if we're plugged into a charging station with a battery, we can open K2 and we can charge using the onboard power electronics. Or if it didn't have the battery, we close K2 and the external infrastructure can charge directly the onboard EV battery. So both the charging station and the EV are both backwards and forwards compatible. So we can prove that concept as well. And the upgradable aspect is actually what we're planning on doing with passenger vehicle market. As I mentioned, quite a number of OEMs now are coming out with vehicles with onboard charging. It means we can already start deploying this infrastructure. So if we took a previous deployment of a 50 kilowatt 400 volt charger, we can simply add a battery to the output and do that switch in switch out thing to either remain as a 50 kilowatt charger for older style vehicles without an onboard DC charger, or when it's a newer vehicle with the onboard DC charger, we switch in the battery, and that vehicle can now charge it at a higher power. So in this case, we can charge up to, well, for an Ioniq 5, up to 160 kilowatts. And the cost is very low. So we'd be looking at about a bill of materials around $2,000 to apply this upgrade, excluding the cost of the battery. So if we could get maybe a second life battery, that's the cost is negligible, then yeah, it's a very low cost retrofit upgrade to existing infrastructure, because no one wants to charge at a 50 kilowatt charger anymore. That's way too slow for a new generation vehicle.
Stefan,
and this is
question: are the Class 8 OEMs talking about putting onboard chargers on those trucks as they come out?
So this is all still pretty new technology. So I would say it's certainly a conversation which is probably being had right now, but there's been nothing public to date. But
and this is said, I'll add in on the classic structure of the trucking industry, and Dave Schaller and others can speak up to say they will build what the customer asks for. Now the customers have to be convinced that this is in their best ROI, right? So if they're a fleet operator and they can reduce their infrastructure costs, especially if it's on their shoulders, they would shift that cost to the truck away from the infrastructure, versus other ones might have a third party who they're leasing everything from and it's already bundled, so it doesn't cost them anything for the charging infrastructure, anything incrementally. And so I think that equation is what determines whether they'll go for this path or not. But I definitely think it will be offered because people are going to bundle things. Right? It's always that bundle, it's over and over again, CapEx, OpEx, and it all depends on who's paying.
Yeah, and customer's always king. I mean, if customer requests it, but I mean, it's also an education thing. I mean, this is, this is new technology. The customer doesn't even know this exists yet, I guess, or the potential is there, because the cost of the vehicle is, if you had a quad powertrain setup and it's a $30 switch per powertrain, that's $120. That's negligible, considering you potentially get then a 1 megawatt charger for free. And that's going to save you $500,000 on installing a 500 kilowatt or a 1 megawatt external charger. So
Stefan,
I think the cost benefit is there.
Can you comment on the impact on MTBF? I mean, can you comment on the reliability impact on the drivetrain? You're going to be running it twice as much, right? So is it going to cut the life in half? I mean, is the grid supply is typically, let's just say there's more transients there. You have to deal with lightning strikes. I don't know how much that gets filtered out through your constant voltage source, but there is going to be an impact. Is it negligible?
It's negligible because, and this is the modeling. So we did some modeling with Infineon. Is that what affects the life cycle of the traction drive is the thermal cycles. So it's always with your silicon switches, it ends up being something like a wire bond break or something to that nature, and that's dictated by how many times it expands and contracts in the thermal cycle. When you're driving the vehicle, every time you accelerate and then cruise and then decelerate, you've gone through a thermal cycle to accelerate, and then it's cooled down while you cruise, and then a thermal cycle while you regenerative brake. So in 10, 20 minutes of driving, you've probably done a couple of hundred thermal cycles, whereas the charging cycle is just one thermal cycle. It's a constant current cycle. So we ramp it up to 500 amps, whatever your charging is going to be, and it remains there for the whole 20 minutes until it comes down. So even though it seems like the drive's been in operation, so you've got a much longer, I guess, hours of use, the thermal cycle's increase is negligible.
Well, there might be some from grid services if you have to ramp down here and there, but yeah, that makes a very strong argument. But what about transients from the grid? I mean, you have a lightning strike nearby. You're going to see transients that you never see driving the motors or doing regenerative braking. It's kind of like being in a bad neighborhood,
Yeah, and that comes down to infrastructure planning, I guess. What sort of surge protection do you have on your infrastructure? If you had a DC microgrid, surely you would want some sort of surge protection because you've got other sensitive power electronics on there. You didn't want to blow up. You've got a charge controller from your solar panels. You don't want to blow that up, and then if that blows up, it might blow. Your solar panels might catch fire or something. I don't know. But everything's going to be affected.
The rail source is particularly interesting because those guys tend to spark on the catenary a bunch. I mean, it does seem like a gold mine, but there are going to be some issues. It's interesting though. Thanks for the thermal argument. That's a big one.
Yeah. Okay. Sure. So here's another topology which we've been sort of thinking about, which is a way to get galvanic isolation between vehicles. It's basically a continuation of the previous topology where you've got a converter and then a battery which you could switch in. But in this case, we're doing it from a common DC bus, and these are isolated DC to DC converters. So something like an Allen Con Boss, if you had one of those and then you have a battery, then you're basically creating lots of little boost outlets. And then you could have a depot with maybe 10 outlets with each one of the vehicles being galvanically isolated. And each one having its own little battery as a power buffer. And this has some other interesting benefits, like you can cycle power between the DC to DCs. If you're charging a vehicle at this top location from the other ones, you could use the DC to DC to push power back into the grid to avoid drawing from the grid connection. So there's all sorts of opportunities, and there's certainly we've got a lot of ideas in this space, and very interested with working with anyone who's sort of looking at building out next generation infrastructure, either as a trial or as a commercial application. And this was just the last slide. Something else I just threw in is the ability that, just because I'm focusing on charging from DC doesn't mean we can't also do AC. So if you had something like a combo plug, we can bring in AC, which I've been told on the 6mm pin, we can get 90 kilowatts apparently from that. So you could potentially add a 90 kilowatt rectifier before the DC to DC, and then you've got your standard, you would do something like a synchronous rectification here with power factor correction, and then you would do the DC to DC would be your constant voltage or constant current for the charging current for regulating the current going into the battery.
Just a small suggestion. This is a great slide, by the way, just making the battery a different color to show its higher potential, perhaps a purple or something.
Yeah.
I assume you're always using the power conversion in the vehicle as a boost function, right?
What, the DC to DC or the rectifier?
The DC to DC repurposed drive inside the vehicle.
So it could be either a boost or buck. I mean, maybe it's better to do a boost and then a buck, and then you've got no discontinuous currents on the output. If you do the buck on the output and the boost on the input, then you've also got no discontinuous current. So maybe from an EMI perspective, a boost buck conversion would be better than a buck boost, if you get me. But you could do it anyway. It's complete flexibility.
This is Ali Reza again. The only thing is if you're putting that AC/DC on board, those PFC inductors, they're going to be huge. They're going to add significantly to the weight of the vehicle index if you're doing 150 kilowatt. I mean, you saw the patent I-70 we have. In that, you don't need those PFC inductors.
So why is that? I mean, we could use that style of rectifier. You're using a buck rectifier, is it not?
Yeah, ours is simply everything is passive. In active components, we don't have any passive component except EMI filter chokes. And then we are using the motor windings as a PFC inductors.
Yeah. Okay. Yeah.
So yeah, there's no additional inductor, so no passive components. That's why it's going to be very tiny, even if it's 100 kilowatt.
Yeah. Well, we can do the same. So the only difference is that we've got a capacitance between the output of the buck converter and the input of the boost converter, and that may affect the PFC quality. I'm not sure. We'd have to look at that.
It's a little bit different. So our approach is a little bit different than your approach. I mean, we can talk more offline.
Yeah. I don't necessarily see a reason why it wouldn't work though. Combine the two.
The question is if you need insulation in your AC/DC conversion. That's a choice, I suppose.
Well, if you put insulation, sorry, do you mean insulation or isolation?
Yeah, good question. Do you live in the US or in the UK? I would say you would need at least basic insulation.
Yeah. So I think going from like the trolley bus industry, they say you want double insulation when it's a unisolated system.
Yeah.
And in this case, it doesn't make sense to make this AC to DC rectifier with an isolation barrier because then you're just building an onboard AC to DC charger anyway. It becomes impractical to have a 100 kilowatt isolation barrier on board. You might as well then just go for the off-grid isolation. In my opinion.
Well, there are already vehicles on the market that don't use insulation, so I suppose that makes sense.
Yeah. So the Zoe, for example, doesn't use isolation. There's a lot of trolley buses and stuff that don't use isolation. I know that. But yeah, it's just an option. I mean, my focus has been on the DC because the traction drive is going to be rated at a couple hundred kilowatts. If you're only operating it at, the standard or the Type 2 is 43 kilowatts or 52 kilowatts in the US at 480 volts. You're not operating the drivetrain electronics to their full potential. If you've got a half a megawatt worth of power electronics and you're charging at 40 kilowatts, its efficiency is not as high as it could be because the electronics want to push harder. And the DC standards allow for, we can go up to 1 megawatts with a pantograph or even the HPC VC standard, the new standard.
Yeah, so just from that, if in the future you say MCS, that's the new handle. Just because again, when you read stuff in old writing, it says HPCCV, but just MCS is the new one, and then just Stefan from Australia being aware that there's IEC and SAE activities to standardize that, but that's the name.
Yeah.
So keep going. I just want to remind people that the meeting officially ended, half an hour ago, but because the topic is recorded, it doesn't matter when the meeting ends. The materials are still. So we talked about what we were supposed to talk about today. We had a meeting discussion, but let's just keep going. I'm just saying, it's going well. Keep going.
Okay, well, that's the end of my presentation. I actually tried to slim it down and deleted a whole bunch more slides. But I guess what I wanted to say now is that, we'd like to research these topics more. We'd like to build prototypes. We're open to working with anyone and everyone. There's, once you enable this DC charging on board, which is, as you've seen, very low cost, we can do it for, in the tens of dollars and a couple hundred grams. It's negligible on a full-size truck. Then it opens up a whole range of possibilities. I mean, I've explored so many possibilities in this, but there's many more that potentially could be done. And I genuinely think this is the future of charging. I mean, we see passenger vehicles going that way with mass market. Hyundai alone are going to have 1 million vehicles on the road by 2025 with high-powered onboard DC chargers. It's just ready to be exploited. Why continue the trajectory of spending $100,000 on replicating those components off board when the vehicles can easily use them on board? So I think eventually it will go this way. It's just it's a big ship and it's hard to move. We've been building external chargers for 10 years.
In the context of safety, right? I can visualize this as a rugby scrum. There's going to be a whole bunch of people locked elbow to elbow, pushing the pile 1 foot to the left, and then the other pile pushes it a foot to the left, back to the right, and the pile moves inches when there are thousands of pounds of effort applied each side. So I definitely see safety and economy arguing with each other.
Yeah.
Stefan, can you comment on using this approach for an off-board three-phase AC supplied directly? I know we've got off-road applications going up to 500 kilowatts from an AC input just using the drive electronics. I don't know that they're commercial yet, but I mean, of course, you cited BYD. I don't know the differences between. There was some offline discussion about the differences in their approach, but
it's a shame. Greg Reese was on, and that was his product. So maybe in the next meeting he can talk more about what they do for mining and marine.
Okay, all right.
Yeah, I did have up the topology of the BYD, but I've since deleted it. But the BYD solution doesn't scale that well because they actually have to add a lot more. They add a three-phase sine filter, like a choke and boost inductors to the solution. They're not using the magnetics of the motor of the machine. So as Ali Reza said earlier, that adds a lot of cost and weight and space. I mean, the chokes are the biggest component. You don't want to be adding extra inductors if you can get away with it. But I think you were specifically talking about off-board.
No, as Ted mentioned, the mining and off-road guys are doing very high power, and I don't think they're adding any more magnetics on the vehicle. I don't know anything about the details of how they're doing it. I just hear them talking in the SAE meetings about the signalings that they need on the CAN bus standard. But I know it is being done. So
yeah, it's going to go that way. It'll go that way. In mining may move first because it has less maybe regulatory hurdles, especially when it's like a mine site in the middle of nowhere.
Well, my understanding is they're using the same technology in their stationary solar inverters that they use in I don't know how they're playing in both those markets, but they play in heavy duty off-road equipment as well as stationary stuff. So.
Right. So again, just an example of Caterpillar. Caterpillar does, generation DER. They're in that market in a big way, and they're leveraging the components that they build for each side of a microgrid and a mining hauler. And the same with Wabtec and GE on the big mine trucks are the same thing they use in the locomotives. So there's a lot of leveraging between industries.
Interesting. Didn't know Caterpillar was doing solar.
It's diverse, right? It's a global company. They build stationary generation, they build PV, they build microgrids, they do. And again, once Komatsu and somebody else comes out, it's escalation, right? When somebody introduces a new product, they all have to match, at least they lose market share.
Well, yeah, and GE does giant, multi-megawatt wind machines and locomotives and jet engines for that matter. So, yeah.
Is anyone
it's all good. Go ahead.
I was just going to mention the charge-on innovation by BHP and Rio Tinto and a few other of the big miners talking about how they need 400 kilowatt hours deposited into a dump truck every cycle. And then when you add up the opportunities for that, so they've got like 40 seconds of dumping, 20 seconds of queue time, 50, I don't know, some other seconds of loading. Like it only ends up being like 3 minutes that you have in total across all these opportunities to give it 400 kilowatt hours. So it ends up being you need like 6 megawatts. So that's going to be an interesting project to see who responds to that and is able to meet that target.
Right. We'll see if, like I said, Jim Adriatis from Kevitech and Greg and others on this distribution list to see if maybe we have a mini panel on that one, which is here's what big looks like. Let's see what applies towards medium duty and heavy duty on road. Because like I said, there's the scaling, there's leveraging, and then again, some companies own assets on both sides, where they can just take it from one part of the company and apply it elsewhere. I got to get going to other meetings too. But going back to last call for any questions, really good. I want to say thanks for putting all these slides together. It was, again, I know what it's like to have to sacrifice on your best slides are the ones that are on the floor, but you can only have so much. The basket can only be so full of materials. The last call.
Well, I'll just say one last thing. I'll encourage any of the OEMs that sort of are interested in this technology to talk to their drive supplier about it, because it's the drive supplier that has to provide this technology for them. So they need to request this feature, or even the end user of the truck or bus or whatever, they need to request this feature from the OEM as well. So someone needs to say, hey, I put my hand up, I want to save money. Someone please spend the engineering effort to put this switch in, because without a kick up the bum, no one does anything.
Oh, and that test bed that you put in there, I definitely think, Manish and others from, DOE kind of know that there's always room to explore ideas, and the commercialization is the second. It's kind of like baseball in the follow through. You can swing at the ball, but you got to swing through the ball, not just at the ball. So it's good to see new ideas, and again, not to keep using baseball, but pitched, right? If you keep doing the same thing in the same way year after year, it stifles innovation. Great. Okay.
Just one last thing. You mentioned all of the 800-volt architectures that have a high-power DC to DC converter to step up from the older 400-volt stations. I believe there's at least one major OEM that's actually just switching around the modules in the pack to rearrange them from a 400-volt pack, from an 800-volt pack when they're driving to a 400-volt pack when they're charging. So I don't think that big converter is the only approach out there.
Yeah,
it's just it's a whole pile of contactors to rearrange.
Yeah. And the ISO 26262, I can imagine, would be quite difficult around that as well.
It's always difficult.
I didn't mention them. So that as far as I'm aware, GM are doing that. But I didn't mention that because the Hummer EV it's not out yet. So there's not an 800-volt vehicle on the road that is doing that yet. And so it hasn't gone through homologation and whatnot.
Interesting. Thanks for the tip.
No worries.
Yeah, and again, when you get 200 kilowatt hour and a 9,000 pound curb weight vehicle, it's like drinking a Diet Coke after eating a pizza. It's so heavy and so huge. It's over $200,000. It's a huge truck for passengers, right? It's not even pulling a fifth wheel. So anyway, that's my input. So thanks for everybody sticking to the end. I think we're going to wrap this up. And like I said, thank you for losing sleep, Stefan, from Australia. And we'll kind of have maybe a revisit at the start of the next meeting.
Thanks everyone.
Cool.
Yeah, this is a hugely important topic. Thanks, Stefan.
No worries.
Okay.
Thank you.